I'm Flip Phillips from Skidmore College, soon to be Rochester Institute of Technology. I am talking about classroom projects that we've done with Mathematica. The title of the talk is Apples and Oranges, Computational Thinking with Colorimetry. We're going to look a little bit at how we developed some project-based courses where we combine hardware, data acquisition, a little bit of the device toolkit, some machine learning of the resultant data, and the student experience through that whole thing. So hi, I'm Flip Phillips. I'm from Skidmore with the replacement rule of going to Rochester Institute of Technology. I'm going to talk a little bit today about the how we do a computational thinking-esque kind of class. And it's a project-based class, and I'll kind of walk you through it. Okay, there we go. So it turns out, so we've been offering a course like this since the late 90s. And it turns out a lot of people, it's like, oh, psychology department, computation, all these other things. I am surprised to notice that SCIP, which is the Society for Computers and Psych, has been around since 1971. The people who do this kind of thing, we have a whole journal related to this, BRM, and it's a high-impact journal, and it's a research methods journal. Over the years, it turns out that psych and neuro have been adopters of computation for a lot of different reasons. Stimulus presentation, obviously analysis and things like that, a lot of computational modeling. But it turns out, hold on here. Over the years, we've taught this class with either specialized software of some kind, so we've used like RSVP as a stimulus presentation system, some neural network software. We've used our own experimental language that has that wonderful self-referential, EEL stands for EEL experimental language. We were talking about that. We've done some world building things. There's a system called Psychopy that we've used. We've done a lot of robotic-based stuff as well. We've used Python. More recently, we're using Mathematica. And the goal of the class isn't so much to teach people about what it means to program as much as it is for teaching people about stimulus generation, teaching people about tools for analysis and tools for control. My main background is in what's called psychophysics. Those of you who are physicists may now, tut at the idea. But it turns out that, and those of you who are perceptual neuroscientists may now cheer wholeheartedly, in that it turns out that, and Fechner here, who was both a philosopher and a physicist, made this observation that, and he's sometimes, by the way, seen as the father of modern experimental psychology. And he made this observation that the physical world is not perceived in a uniform or even consistent way. So things you measure in the physical world, people's ability to detect differences in weights or differences in brightness, loudness, color, things that are easy to measure physically, perceptually doubling the weight of something does not double its phenomenological experience of weight. Doubling the number of photons coming out of there doesn't double the amount of light. So Fechner was very big on this whole idea of physics exists in the world, but the way the brain interprets it is not always consistent with that. This is the most classic example of this I can ever show people. This is Roger Shepard from Stanford. These two tables, and again, I'll show you this and you still won't believe me. Those two tables have exactly the same shape of a tabletop. And I realized later, and I didn't, it kills me from the last talk, I should have used flip view for this, just as, no, I should, yeah, anyway. Yeah, thanks. But those tables are exactly the same size, exactly the same shape, right? And so, and again, physically, you go measure them, they're exactly the same. But when you look at it like that, it's totally inconsistent. Now, this is, some people call these things an illusion. Most of these things are basically misperceptions, and I wouldn't even call them misperceptions. They're correct perceptions. It's just that you don't do the right stuff in your head when it comes to measuring angles and measuring distances. The fact that this is embedded in 3D, makes a pretty big deal about this. So in this class, it's been a project-based class, like I talked about before, and these are just some of the projects that I pulled off of the thing. Some of the students were upset that the face recognition algorithms do not recognize cartoon faces, and now the image identify recognizes a very small set of a taxonomy of certain faces. So one group wrote a cartoon face recognition system, which I thought was beautiful. Well before we had this ability to do things with video like we have now, we've done a lot of rat behavior monitoring, so we wrote our own software for using FFmpeg and reading things in and out of the language. Had a student write a whole series of genetic algorithms for a creature that could sense its world and basically evolve in its world. Lots of visual system simulation of other animals, so animals that have 3, 4, 5, some dozen different photoreceptors, simulating kind of what that is. Modeling prosopagnosia, so face blindness. So it's always kind of ironic. You've got these face detection algorithms, but then there are certain neurological problems that cause you not to be able to see faces. So they went back in, took a face recognition algorithm, blurred the faces in systematic ways, and then retrained the algorithm. And it turns out that just like with people, does anybody, prosopagnosia, does this mean things to most of you? Yeah. Anybody have it in here? It's somewhat weirdly common. Can always use it to get out of, you. And one of the ways that people with face hope is they use things like hair, or they use things like, the fact that he always wears white shirts, or the tone of voice and things like that. And when they programmed, they used a classic image recognition, face recognition network, and they found out that whenever they fed it test things, if it was wearing similar clothing to the person in the picture, it would identify it as the person in the picture. So, or different hair. So all blonde-haired people. This is Seeley here. Everyone fed into the algorithm that had blonde hair was Seeley. So I thought that was kind of a fun thing. I've had other students in this class from different departments. We had some political science students who were modeling things, and they were trying to predict. They wrote this huge network for predicting voter behavior. This was my favorite: a business student, a computer science student, and I can't remember the third. I think he was an English major. Wrote a simulating asteroid impacts and whether it would eliminate the population of the Earth. So it's not all psych modeling. So, yeah. So the Spring 2000 project, I had a smaller class than I usually did because of scheduling conflict, and so we decided to do one main project together. Yes, sir? Yes, but I'm going to talk now a little bit about what the idea was. I'm going to just give you an example of a longer term. That wasn't just one thing. It was the whole class. That was the end result. I can see it. No, that's where I'm going. Yeah, that's the whole point. So I'm going to talk about this project. So the project was, again, broad familiarity with computation. So programming and the whole idea that programming is not this is from a syllabus. You don't learn how to program, and at some point it's not even worth thinking about it that way. Secondarily, the idea of data. What does it mean? How do we use it in our field? And one of the things the students were interested in this particular incarnation of the class was what they wanted to use some hardware. And so we created this project, and this is actually the kind of the, spec sheet for this thing. but they wanted to create a system that could learn to identify and recognize different types of fruit. It started out because, of course, like all good college students, it's like, well, we got some things we want to measure, and one of the students had, they stole, but they took a bunch of fruit from the dining hall, had a backpack full, basically, of fruit. We dumped it out on the table, and we started measuring it. So the idea was that we were going to collect the data, do a little bit of hardware, do a little bit of machine learning. That was another thing they requested. And then we were going to try to deploy this thing. So how do we do this? And so to the computational thinking part here. The idea, and this is, I've been, and not just because for the ironic reasons, I've never been a big flipped class person. And for those of you who know what that is in general, the idea is you give people work up front to do. We used to call it homework, but then instead of doing that work as just adjunct to the stuff you're supposed to learn, you do the work and then you come in and actually apply the work in class. Flipped classrooms are far more detailed than that, but we basically used the EIWL chapters. Then we used Jesse's streaming notebook stuff this semester. Thank you again. Yeah, oh yeah. And yes, indeed, yes. Sorry. Because the way we usually do this class is we pass around, we're in a room like this, and here's one of the students who has stolen the fruit, and we pass around a video cable. People kind of patch in, and then you display it back here on the board. But so this time around, though, we used the shared notebooks, and then we also would record my interaction. So the idea of the flipped classroom is you're having trouble with this, we all work on this together. That's where the shared notebook stuff comes in handy, right? Student X says, I'm having trouble with this part. You just deploy that to everybody in the classroom, everybody works on it, everybody can kind of share the results back and forth. But then I use ScreenFlow, and then Skidmore uses Ensemble to distribute things, so we had basically video feeds of the classes that students could go back and watch later. And then finally, because I come from a design school in undergrad, we used the Charette System, which is the way you do design review in like architectural design or product design, which involves it's a group critique kind of thing. So the way we started off was basically with the idea of a photometer. Photometer measures the number of photons, the radiant flux over a certain surface over a certain amount of time. And there's an SI unit, and we could probably get a full set of detail on this. But the idea was we used an Arduino, taught them some very basic electronics, had them go out and learn a little bit about what a voltage divider was, things like that. And then we also used commercial measurement equipment, so we had to write an external system for getting the data from that in as well. That I just have in my lab already. And the idea, and here's some data from one of these things, was to literally try to calibrate a photocell against the actual amount of light coming in. And then we did a similar set of things where we then did the psychological part of it, where we had people estimate the magnitude of the brightness of the light and then compared it to this also. So the idea in this whole lesson, this part of this lesson, was to get them to think about the idea of getting information into the computer and then calibrating that information against some kind of truth or some kind of ground truth or something along those lines. Again, there's a billion different ways to do that as well, but at least we could do it here. And then to use that to perform experiments downstream. They built kind of a faux colorimeter from there, but then we went ahead and used, and Suba talked just a minute ago, he talked about one of these types of things. We actually used a real 6-channel spectrophotometer chip that instead of giving you XYZ or a location in color space, actually gives you the magnitude at 6 different bands of visible electromagnetic radiation. We used the Arduino to, and we basically, this was a good chance for them to learn how to do procedural coding at a very basic level, so they wrote a little Arduino code. And again, they took measurements, they then took those measurements and computed responses and things like this. So the idea was from the physical world, going to gather that data, we're going to then go in and estimate spectra of different types of fruit, and the whole idea was, well, maybe we can use that right there, or some vector derived from this as a way to identify different types of fruit with our little scanner. It turns out, though, that if you do that, and with a pretty good amount of data, you end up with not very good classification. Those would all be bananas down there at the bottom, and you can see it's only about 60% solid. So we had some other things to look at, one of which was some friends of mine at Gießen had built this gigantic database of fruits and vegetables. They used a camera that has 400 bands of, so it's a hyperspectral camera. It's got 400 bands at 1 nanometer resolution, so they're able to just sample the bejesus out of these fruits, inside and outside. It turns out that the good news for that is that here in L and M cones, these are your what we would think of as green and red cones in the visual system. The L and M cones, there's a nice way of classifying a fruit based on the relative amount of excitation of that particular set of cells in your retina. And again, neuroscience class, right, ideas, look at this, see what's going on. That's the good news. The bad news is that that's all 42 fruit. That's the spectra of all 42 fruit. And trying to discriminate fruit based on their spectra alone, because you'll notice it's like a literal traffic jam when you get out here to the right, it's really, really hard. Taking a single scan of a single fruit and trying to figure out what it is based on its actual spectral content, it doesn't work very well. So the students built an autoencoder. So some students wanted to do some machine learning. They taught the other students what they had known a little bit about this basic idea of taking a piece of 6-channel data, mapping it to these 400-channel data measurements, and then testing. They did this is all from their notebook where they tested the network against itself, and then they created this association between the 6-channel data that we had, and they were able to get the thing to literally from a piece of 6-channel data where you saw before banana, apple, banana. They were able to get almost 100% reliability by using the hyperspectral data as their as the space that they were projecting the little 6-channel measurements into. So, and there's the little machine they built to do it, complete with fruit-related buttons on the thing. It was 98% accuracy. We couldn't find any blue fruit, but even though George Carlin was not available. No, blueberries are not blue. There's a whole bit on this. So, the original idea, what they wanted to do, and we didn't have time, the dotted lines are what they originally wanted to do, is they wanted to build, and we've got the little case, we wanted the students to be able to digitize fruit in the dining hall, use the Wi-Fi, because there's several of these Arduinos that have Wi-Fi, so we'd use the photometry chip, use Wi-Fi to send it up to a data drop, and then basically use that to build the spectrum database that we would then later on use to build the autoencoder. And we basically ran out of time, and since Suba is not here, we had trouble with, there were some implementation details with the microcontroller kit that allowed, the Wi-Fi kind of setup and the data drop setup wasn't working. But still, the whole idea was that we were able to measure bananas and predict bananas with a reasonable amount of reliability. So, real quickly then, it was basically a 15-week class for upper-level neuroscience. So when I say computational thinking, a lot of you, and I do not dispute this at all, I would rather, if I'm going to teach a true computational thinking class, I'd like to teach it to freshmen, and it would be much more removed from, it would be a little more removed than this. But this is an upper division class that is optional, and the goal is to make the students aware that there are techniques, methods, that we use in our field in different laboratory settings that are basically computationally based. We built a simple spectrophotometer, a photometer. They learned how to do really basic Arduino and electronic things, and at least were exposed to procedural programming. Then they used Mathematica, and they were able to build a simple classify. They used the classify function. They did some machine learning, and they did basically an end-to-end, acquisition to prediction kind of a thing. The thing that's important, and again, this is kind of goes without saying, didn't teach them how to be programmers, didn't teach them how to be engineers, didn't teach them to be makers either. This is kind of a big fad, especially where I am. It's like everyone has to be a maker. It's like, no, that making is, and again, nothing against being makers, but that's part of it. It's a creative process that feeds into this, but it doesn't necessarily define this. The goal is we got to solve a problem. I need to acquire data about where a rat is in an open field maze. I got to figure out whether the rat is posing in a particular position. What do I do? So it did teach them to, think, I would claim. And more importantly, it taught them how to go after the documentation in Mathematica, which again, I continue to think is wonderful. Taught them how to collaborate and kind of solve these types of problems. My favorite anecdote from this is with respect to the manuals, and I don't know if any of you, if you teach students, one of the things you notice is that they'll go to Google for everything. And the beautiful, whoever's in charge of this at Wolfram, whoever has done the SEO, pretty much if you Google Mathematica list plot, it takes you to Wolfram's page. And so therefore they're reading, and I just love the confusion on their face. They're reading the Wolfram documentation in Safari or whatever, and then you show them that it's built into the thing and they don't need to go there, but they would still rather go over and type Google and go to this page, right? And so thankfully the same documentation is out there as is in here. But so like I said, again, not a computational thinking class at its base, to get to your point, but a way of thinking about it within the domain of psych and neuro. So that's all I got. Thank you for your attention.